Hey math kids, today we're going to talk about properties of complex conjugates, and yeah, so let's talk about some terminology. So if we have a complex number z and there's a little asterisk like where an exponent would be, that is called the conjugate. Okay, so if we have a conjugate and then we take the conjugate of it, it's just going to be the original one. If we add two complex numbers together and we take the conjugate of their sum, that's the same as the sum of their individual conjugates. Okay, same thing is true with subtraction. So if I just went through, let me make this smaller. If I just change that to a subtraction sign, it's also true. Okay, if I change it to multiplication, it's also true. And if I change it to division, it's also true. Okay, but obviously for division, the bottom cannot equal 0. Okay, if we do z to the n and we take the conjugate of that, that is the same thing as taking the conjugate of z and raising it to the n. Okay, and n has to be a positive integer. And then if we add something with its conjugate, it will be real. And if we multiply something with its conjugate, that will also be real. All right, let's go through a couple examples. So z1 plus z2, and then we take the conjugate, and we want to prove we're just going to prove this property to be true. Okay, so we're going to say that z1 is a plus bi, and let's let z2 be c plus di. Okay, which would mean that the conjugate of this one would be a minus bi, and the conjugate of this one would be c minus di. Okay. So if we add both of them together, if we add z1 and z2, so z1 plus z2, that's going to be a plus bi plus c plus di, which we could simplify to a plus c plus I b plus d. Okay? And then if we took the conjugate of that, that's going to be a plus c minus I b plus d. Okay, so the left side of our equation is going to be this, if we approach it that way. Now, if we just take this plus this, we're hoping it equals this. So z1 conjugate, z2 conjugate is going to be a minus bi plus c minus di. And if we do that, we group the a and the c. They're both positive, so it's still going to be a plus c. And then we can take out a negative I from this and from this, so that's negative I. We're left with b plus d. And since both these are the same thing, we prove that that's true. Okay, now z1, z2, we're going to prove that this is true as well. We'll approach it similar. So z1 is a plus bi. Z1 conjugate is a minus bi. Z2 and Z2 conjugate. C plus di. C minus di. Okay, on this side we multiply the originals first. So we're going to say z1, z2 is going to be a plus bi. C plus di. Multiply those, that's AC. Multiply those, ADI. C, let's see, BCI plus BDI squared. Alright. Now, remember that I squared is negative 1. So we change the sign right there. So the real part on this is going to be AC minus BD. And then the imaginary part is going to be AD plus BC. Okay? And then if we take the conjugate of that, so Z1, Z2 conjugate, that's going to be AC minus BD minus IAD plus BC. Just changing this sign right here. Alright, so that's the left side of the equation. We're hoping the right does the same. And if we just multiply these together, so A times C is AC, A times that is negative negative ADI. That times that is negative BCI, and that times that is positive BDI squared. Okay? We want to pull out, this will change the sign like it did last time. And then the real part is going to be AC minus BD. So that's good, because that's the same. So we got that. And then we can take out a negative and an I. And then we're left with AD minus BC. AD, plus. Because we took out the negatives. Alright, both those are the same, and so we proved that that's true. If you need additional help, please come to Math Lab. Until then, calculator.